Is Fourier transform and Laplace transform. This is the basics for the beginners. In this we are what is Fourier transform, what is Laplace transform, why we are using Fourier transform and why we are using Laplace transform, and when to use Fourier transform and when to use the Laplace transform, what are the formulas for Fourier transform and Laplace transform, and what are the properties of Fourier transform and Laplace transform, and what is the relation between the Fourier transform and the Laplace transform, and the implementation of Laplace transform and Fourier transform in various applications and frequently useful formulae we are going to see. Now, what is meant by transform? Transform is nothing but mapping between the two domains, and Fourier transform is an operation that transforms data from the time domain into the frequency domain. And why we are using Fourier transform? Why not Fourier series? Because the Fourier series is for periodic signals, whereas Fourier transform can be performed for non-periodic signals as well. Let's transform them. Laplace transform, it is named after an inventor Pierre Simon Laplace. It is an integral transform that converts a function of a real variable to a function of a complex variable. If you look at the formula here, g of t e power minus j 2 pi t dt plus integral e power minus at, which is a complex domain. When both of them are combined, it will give us a Laplace transform. Extending the Fourier transform to the complex domain means it includes the Laplace transform as a special case of Fourier transform. And then transform to analyze the signals in another form, and to maintain the information on amplitude, frequency and phase, and to translate the signal to frequency domain. Any waveform can be represented as a sum of sinusoidal signals by using Fourier transform, and the differential equation solutions must be either exponential or sinusoidal, because the derivative of exponential is the scaled version of itself and the second derivative of sinusoidal is the negative scaled version of itself. Because of these two reasons, we will be using in differential equation solutions must be either in exponential or in sinusoidal. To detect the small changes in the signals, we need Fourier transform, and Fourier transforms give us those amplitudes and offsets decomposing the original wave. Laplace transform then. The Laplace transform reduces a linear differential or differential equation to an algebraic equation, which can then be solved by formal rules of algebra when under certain initial conditions are given. Here, differential equation of time domain form is first transformed to algebraic equation of frequency domain form. After solving the algebraic equation in frequency domain, the result then is finally transformed to time domain form to achieve the ultimate solution of the differential equation. Whenever there is a need to break down a complex time domain signal into simple sinusoidal signals in frequency domain, then we can use the Fourier transform. And roughly, Fourier transform is nothing but a tool to visualize any signal as a sum of sinusoids. It depends on initial conditions and boundary values and restrictions, but for finite systems and linear equations, Fourier transforms gives you transformation from linear differential equation to matrix form. And the Fourier transform is an important image processing tool which is used to decompose an image into sine and cosine components. Laplace transform, it is a tool to analyze the stability of the system. When there is a need to handle exponentially growing signals or exponentially decaying signals, we need to use Laplace transform. To capture the transient behaviors of the systems, we need Laplace transform. And the Laplace transforms give solution in terms of decaying exponents. Different formulae for Laplace transform and Fourier transform. For Fourier transform, the Fourier transform of g of t, which is called a g of f, is given as an integral from minus infinity to plus infinity g of t e power minus 2 pi f t dt, whereas in Laplace transform it will be in s domain. F of s is equal to integral 0 to infinity f of t e power minus s t dt. If you see here in Fourier transform, the limit will be from minus infinity to plus infinity, but for Laplace transform it is from 0 to plus infinity. And for inverse Fourier transform, we just need to take the inverse of it. Fourier inverse of g of f is g of t, which is the integral from minus infinity to plus infinity g of f e power j 2 pi f df. Inverse Laplace transform, f of t is equal to 1 by 2 pi j integral of sigma minus j infinity to sigma plus j infinity f of s e power st ds. What are the properties of Fourier transform? If the Fourier transform of x of t is x of omega, and the Fourier transform of y of t is y of omega. The linearity property comes into picture as a x of t plus b y of t. When the Fourier transform is taken for this, it will be a into x of omega plus b into y of omega. If you take a time shifting property, x of t minus t naught, it is shifted by t naught. The Fourier transform of this will be e power minus j omega t naught x of omega. If we go into the frequency shifting property, frequency is e power j omega naught t into x of t. The Fourier transform of this will be x of omega minus omega naught. There is a shift in omega naught in the frequency domain as well. And when we come to time reversal property, x of minus t, the Fourier transform of x of minus t will be x of minus omega. And the time scaling property, x of at is equal to 1 by mod a x of omega by a. Differential property, which are very important property, is differentiation of x of t. When the Fourier transform is taken for differentiation of x of t, it will give j omega into x of omega. And if we are taking for n signals, t power n x of t by dt dx power n, the Fourier transform will be j omega whole power n into x of omega. If you take a integration property, integral of x of t dt, the Fourier transform of integration is 1 by j omega x of omega. If we take to the power of n integrals, if you are taking j omega will be to the power of n, 1 by j omega whole power n x of omega. If we take a multiplication property, x of t into y of t, the Fourier transform of this will be give a convolution, x of omega convolution y of omega. If we go to the convolution property, x of t convolution of y of t, the Fourier transform of this will be 1 by 2 pi x of omega into y of omega. Come to the properties of Laplace transform, and the Laplace transform of x of t is x of s, and the Laplace transform of y of t is y of s. Coming to linearity property, Laplace transform of a x of t plus b y of t will be giving a x of s plus b y of s. If we go to time shifting property, x of t minus t naught gives e power minus s t naught x of s. If you observe here, in the place of j omega, s is written here. It is the transformation from j omega to s domain, frequency domain to s domain. Frequency shifting property, e power s naught x of t, the Laplace transform of this will be x of s minus s naught, it is shifted by s naught. And the time reversal property, Laplace transform of x of minus t gives x of minus s, and the time scaling property, x of at gives 1 by mod a x of s by a. Property, Laplace transform of differentiation of x of t gives s x of s minus s x of 0. If it is to the n number of signals, d power n x of t by dt power n, Laplace transform gives s power n x of s. Integration property, integration of x of t dt gives 1 by s x of s, and n number of integrations gives 1 by s power n x of s. Multiplication property, x of t into y of t, the Laplace transform will be 1 by 2 pi j x of s convolution of y of s. And if we come to convolution property, x of t convolution y of t gives x of s into y of s. These are the different properties. Relation between Fourier transform and the Laplace transform. In Fourier transform, we use sine waves of constant amplitude to represent a signal. With this way of representing signals, we cannot represent few signals. This is why we need Laplace transform. Here we use sine waves of varying amplitude in time to represent signals. So Fourier transform is a special case of Laplace transform. By the formula, we use s is equal to j omega, it is the Fourier transform. S is equal to a plus j omega, it is Laplace transform. Extending the Fourier transform to complex domain means it includes the Laplace transform as a special case. Of Laplace transform and Fourier transform in various applications. Fourier transform is used in wide range of applications such as differential equations analysis, in quantum mechanics, signal processing, image analysis, image filtering, image reconstruction, and image compression, whereas Laplace transforms are used in circuit analysis, proportional integral derivative controllers, DC motor speed control systems, DC motor position control systems, second order systems of differential equations, whether they are underdamped, overdamped, or critically damped. So these are the different various applications. Very important formula in Fourier transforms. let us see that Fourier transform of f of t minus t naught gives f of omega e power minus j omega naught. F of t e power j omega naught t gives f of omega minus omega naught. F of alpha t gives 1 by mod alpha f of omega by alpha. F of t gives 2 pi f of minus omega. From delta of t, the Fourier transform of delta of t, what is the impulse response Fourier transform? It is 1 e power j omega t 2 pi delta of omega minus omega naught. Sigma of t 2 by j omega d power n by dt power n f of t j omega whole power n f of omega. Integral of minus infinity to dt f of t dt f of omega by j omega plus pi f of 0 del of omega minus j t whole power n f of t d by d omega power n f of omega minus a t u of t 1 by a plus j omega e power minus a t 2a by a square plus omega square. For unit step signal it is 1 by j omega plus pi del of omega. For del of t minus t naught f of t e power minus j omega naught f t naught e power j omega naught 2 pi del of omega minus omega naught. 1 by t signum of omega. For unit step pi del of omega plus 1 by j omega. Rectangle of t by tau is t of sampling of omega t by 2. A cos pi by 2t rectangle of t by 2 are a pi by t cos omega t by t tau omega tau by tau pi by 2 tau whole square minus omega square. For different trigonometric functions like cos omega naught t, it will be pi of del of omega minus omega naught plus del of omega plus omega naught. For sine it is pi by j into del of omega minus omega naught minus del of omega plus omega naught. For u of t into cos omega naught t pi by 2 del of omega minus omega naught plus del of omega plus omega naught plus j omega by omega naught square minus omega square. Like that we have different formulas. You can go through these formulas once again. So we are going to use these formulas while taking the Fourier transforms of different signals. Coming to the Laplace transform. If you like, you can take the screenshot of these formulas. Transform the Laplace transform of 1 is 1 by s, e power at is 1 by s minus a, root t is root over pi by 2 s power 3 by 2, t power p is sigma of p plus 1 by e power p plus s power p plus 1. So sine of at is a by s square plus a square and cos of at is s by s square plus a square. T sine of at is 2as by s square plus a square whole square. T cos of at is s square minus a square by s square plus a square whole square. If you come to different functions, sine of at minus at cos of alpha t 2a cube by s square plus a square whole square. If it is sine at plus at cos at 2a square s square by s square plus a square whole square. Like that for cos also. For hyperbolic sine and hyperbolic cos also. For hyperbolic sine of at a by s square minus a square and hyperbolic cos at s by s square minus a square. The exponential functions as well. E power at sine of bt is equal to b by s minus a whole square plus b square. Like that for cos and hyperbolic sine and hyperbolic cos also we have different formulas. These are the Laplace transform.